can we considering temporal uncertainty in Gaussian process. So today we are mostly talking about Gaussian process, right? So we talked about spatial temporal hierarchical modeling yesterday, but today we are mostly talking about Gaussian process, a specific process level where we use a lot in PaleoSTEM and in many C-level science. So after we talk about temporal uncertainty, we will talk about spatial temporal Gaussian process. So we are covering the temporal Gaussian process yesterday, but today we are going to talk about spatial temporal. And we'll talk about basics, we'll talk about the kernel design and kernel decomposition, which will allow you to decompose different kernel contribution to, to the final Gaussian process contribution. And lastly, we have two more more advanced section today. It's about interaction with physics-based model. So Gaussian process, if we only use statistical model, there are some properties of physics we are lacking in our model. So maybe we can use the physical model to help us do a little bit better job. And lastly, we will try to replicate an example application by COP 2016. So in that case, you will have better understanding like how this model work in a specific project. And okay, let's start it. So if you have any question, please type on the chat bar, or you can unmute yourself. You can stop me anytime, okay? Okay. So before I start to talk about temporal uncertainty, I want to review a bit about the PaleoSTEM implementation of Gaussian process. So here is a typical code we used yesterday. So first thing you probably want to see is like, okay, first thing we want to record the time. I want to record how many time I use for this optimization. So I want to record the time. And second thing is I want to clear the parameter store. So my optimization wouldn't be affected by previous code or whatever, because we are using a Jupyter notebook environment. So this kind of code cell may be affected by previous code. So I want to clear the parameter store. The first one is I want to use a periodic kernel. So I set a periodic kernel because we are doing temporal, only 1D. So input dimension is 1. And then I just set some, sorry, I see a problem. So the question is, sorry, are we supposed to be following one of the Colab notebook now? No, I just go through it. So I will let you know when do you need to open the notebook today, okay? So I just go through the code example yesterday. So I think everyone can have a better understanding. Okay, how do you define a GP model in PaleoSTEM? So after you define a kernel here, you set some hyperparameter prior for this kernel. You don't need to do that, but if you don't do that, there's no kind of prior information considered in this kernel hyperparameter. So if you do that, you can set some prior information to have parameter in your kernel. So here is the second kernel, which is button 5.2. Here you see that I set an initial value for this to have parameter, but you don't necessarily need to do that. And then I just set the prior as well. And then you kind of combine this. You kind of combine these two kernel together as a combined kernel. Here I use the product, which is kind of multiplication between them, but you can use sum to sum them together. And then you use kind of this combined kernel here to input into your GP model, and the first input is your X value, the Y value, and jitter basically means you add a small value to avoid computational issue. And lastly, you kind of just using this optimization algorithms, SVI means stochastic variation or invariance. And you put the GP model, you specify how many iterations you want to run, and you specify learning rate. So yesterday we are talking about temporal Gaussian process, which is computationally much cheaper. So today we are going to talk about spatial temporal Gaussian process. So it's kind of computationally much more expensive. So sometimes you don't need to run too much iteration. So maybe 200, 300 iteration as an initial test before you running like 1,000 iteration, which may take you a while. Yeah, you will experience this today. And then we are kind of plotting the optimization result to see how does the optimization do. And lastly, I want to print how many times I use for this optimization. So after you optimize the Gaussian process, this GPR is already considering the optimized hyperparameters. So you can use this GPR directly for prediction. So here I just I create a new X values. So it's kind of from 1955 to 2030. Like there's a gap between them. It's 0.05 years. So you can predict continuously for this a new X value, and you should notice that this X value should convert it to double data structure. So this is the model requirement. So model require you to input the new X as a double. It's basically just a data structure, and you input this new X value into this GP model, and you set I want this GP model to return the full posterior or conditional covariance function. So this is the covariance function instead of just a diagonal of the variance of each input value, and then I just convert this to standard deviation so I can plot them. Okay, so this is the basic of GP model in PaleoSTEHM. Hope this makes sense to you. And so lastly, I want to talk a little bit more about our Slack. So I hope you get information of our Slack notification yesterday. So I have already shared the PowerPoint, the paper, and the recording in the Slack. So if you haven't joined them, I encourage you to join them. So I will share more in this Slack channel. And if you have any question about PaleoSTEHM, I will try my best to answer them in that channel. Okay. So first, let's talk about start to talk about temporal uncertainty. So in PaleoSTEHM, there are two ways to consider temporal uncertainty. So if we think about our dating of geological records, you usually have a true age, which is TI here. You can think about that as true unobserved age, and our measurement mean is kind of T hat. So which basically may be radiocarbon mean or median value of your choices, and plus some error model, right? This error model can be normally distributed, as like many of us assume to be normally distributed. In Gaussian process, if you think about that was normally distributed, that was slightly easier. But you can think about that was any kind of distribution of your choices. If you use a Markov-Chain Monte Carlo, we will talk about later. So here we assume it. Here the first method is what we call noisy input Gaussian process. So the basic idea is quite simple. So is that we want to transfer this temporal uncertainty into vertical uncertainty. So temporal uncertainty is in horizontal way. We want to convert this horizontal uncertainty into vertical uncertainty. So the way we do that is we calculate the gradient for each data point. So how was the gradient for each data point, right? and then we use this gradient to convert this horizontal uncertainty into vertical uncertainty. So if you can see here, so if you set an initial hyperparameter here, you get this kind of prediction. Here is like you don't consider horizontal uncertainty, so the temporal uncertainty here. But then if you calculate the gradient and you add the horizontal uncertainty into the vertical uncertainty, you get this kind of prediction. So you see here because here the gradient is slightly higher than here. So here the uncertainty, the resulting uncertainty here is slightly larger. Okay, I hope that makes sense. So here is like okay, you can directly add it, but we want to make it more robust. So usually what we do is we set a initial value and we will do this kind of update of update this horizontal uncertainty into temporal uncertainty for each iteration in our optimization. So here is the initial start. So when we do each optimization, we will update the temporal uncertainty into vertical uncertainty. So the resulting estimate of gradients will be more robust. Okay, I hope that makes sense to you. So it's rather simple. So I will talk to you about how PaleoSTEHM achieve it in our code later. Okay, so the second way is usually what we call the error invariable Gaussian process. So instead of you think about that was transferring the temporal uncertainty into vertical uncertainty or sea level uncertainty. Here is we just directly sample them, right? Because we are doing Markov-Chain Monte Carlo. So you can treat any temporal uncertainty as a parameter. So you set that as a parameter, and you can put your lab measurement of your uncertainty distribution as a prior. So you can set a prior as a normal distribution, maybe from some radiocarbon calibration software like Oxcal, Calib, which give you a mean and standard deviation. You can input that as a prior for error invariable, as you can see here. So for the blue dot basically is the prior I put into. I intentionally make the temporal uncertainty a bit larger so you can have a better idea what is the posterior distribution look like. So then I assume a process level, and then I do some Markov-Chain Monte Carlo. So this error invariable framework will directly sample the prior temporal distribution for every data point. So you can see this orange dot here is the posterior of the. You can see the x-axis of this orange dot basically show you what is posterior distribution of each data age model. So you can see that it's clearly moving around here, right? So in this framework, you will be able to generate a posterior distribution of your age model. It's a good thing. It's a bad thing. It's like maybe you just want to stick on your prior. But this kind of framework will alter your prior distribution of age estimate based on different process level model. So you can imagine that if you're using different process level model, your estimate of your posterior age will be different as well. So it's kind of your own choices. We will go through an example later. So it's kind of your own choices to think about which framework you are trying to use. And you can also like do not let the model to alter your prior as well. So this is something we want to do in the future, but it really depends on what kind of project you are doing. And okay. So another thing about this framework is that because we are sampling the prior distribution for every data point, right? So you kind of increase the parameter size whenever you increase one more data. So it's kind of computational heavy, right? If you increase one more data, you have to sample the posterior You have one parameter to sample. So if you have so the computational load for this method is increased kind of almost cubically. So it's kind of computationally very expensive. So you have a notice it. We will have a practical for that later. Okay, so okay, let's go to our Jupyter notebook. So okay, so if you can open PaleoSTEHM in your Google Colab. I know some of you might not be here yesterday, so if you have any questions, so you can ask Alex. So you can DM to Alex. So he will help you to install PaleoSTEHM. So, but in PaleoSTEHM, if you open the tutorial, there's a day 2 PaleoSTEHM. So day 2 PALSEAworkshop. So if you go here, you do have to reset the environment. Okay. So we can reset the environment by running this cell. It's basically install the Pyro, the probability language model we are using for PaleoSTEHM, and Cartopy, which we will use for plotting. Okay, I hope everyone.
Was anyone not here yesterday? Who's here today?
Yeah, I think some of them might. But yeah, so I hope you don't have any question about. I hope you will be all right with the installation. Have you tried to install it? But it's generally pretty easy. I will try to copy and paste the instruction in the chart bar again. Okay. Okay. So it may take 1 or 2 minutes to set up the environment. But today, because we are doing spatial temporal, so please do not run too much code before I demonstrate it, because I kind of tested yesterday night. It's like the computational burden will crash this kind of notebook in Colab. So please do not run it before demonstrated, because we do need to change the resolution to let it run. Otherwise, it might crash.
Yeah, this uses a lot of RAM too, this notebook. So if you do have like extra stuff open, I would definitely recommend closing that out.
Yeah, so also like if you want to run this kind of spatial temporal Gaussian process for your own project, I encourage you to install this locally. So Jupyter notebook, so Google Colab do not have too much computational resources for you. Okay, so I have. If you see this kind of mounted information here, it's kind of installing good. Okay, so I hope everyone doing well. So let me just. So how about like I will demonstrate it first, and I will give you 5 minutes after that. You can play with it. Okay, but so I'll talk about our code first. So here is like the first thing is I just randomly generate some synthetic data from this true function, and add some temporal uncertainty and vertical uncertainty. I intentionally make the temporal uncertainty really large, so you can have a better idea, like what if we consider temporal uncertainty, what if we don't. Okay. So so here is like we as we did before, we set a Gaussian process, we set a prior, we set a kernel, and we include this kernel and the noisy X, noisy Y into this Gaussian process, and we are using an RBF kernel here. Okay, so I would encourage you to just changing the number of iteration to 200, so you'll run quicker. Because okay, run much quicker. So and then you will be able to see this kind of if we do not consider temporal uncertainty in this Gaussian process, you kind of the estimate is kind of give you a strong bias. So it's kind of the uncertainty range do not cover at all of the true function, right? So then we will try our first noisy input Gaussian process, which is we transfer the horizontal uncertainty into vertical uncertainty. And then the only difference we are making here is here. So here the optimization is what we call stochastic variational invariance optimization. Here, you see here. And then here we are changing our optimization is noisy input optimization. So the only difference is here. So in this optimization, you kind of for each iteration you convert the horizontal uncertainty into vertical uncertainty, and you do need to input x noisy here as the standard deviation of your horizontal uncertainty. Okay, so here I also want to change the iteration into 200. It's to run faster. Okay, and then I plot them. Okay, you see that if we consider the temporal uncertainty in this way, it's kind of the uncertainty range expand a little bit and it becomes smoother because it's kind of smoother in terms of our estimation because if you see this kind of really noisy data, it's kind of natural to get this kind of smooth curve instead of like this kind of curvy original estimate by the original Gaussian process. And then we will use the error invariable Gaussian process. So it's kind of we are sampling the temporal uncertainty directly by MCMC. So how do you do that? So here is like now the model we are using is different. Okay, so imagine here is like we are using a GP regressor for empirical base. But if we are using Gaussian process for sampling horizontal uncertainty, we need to use error invariable Gaussian process. So it's kind of coding in a way that you can directly sample the Gaussian process in your GP model. So in this case, your inputs x value, y value, x noise, your kernel, and your y noise, right? The x noise is represented by the variance value instead of the standard deviation. Okay, so then you can run the MCMC algorithm. We warm up 200 iteration, and let's just run it for 1,000 iteration to get the posterior distribution. You see that to run much slower. It kind of makes sense because MCMC is meant to be slower than empirical base, and you're running the you're sampling the temporal distribution directly, so it's kind of slower. So if you have time, you can now run through this code to see, because it takes a while. Okay, I hope you are doing well with your environment. So if you have any question, you can ask me now. Meanwhile, we're setting this, we are running the MCMC. But if you have any question about like the code setup or like the syntax we are using here, just let me know. Okay, maybe I think it's kind of straightforward to me, but like maybe it's kind of confusing to you. Maybe you can let me know. If you here just everything is the same, you can set the kernel, input data, and optimize the model.
I have a question since
Sure.
we're watching the bar move.
Yeah.
I was not here yesterday, so maybe this is part of PaleoSTEM already, but have you all considered implementing or creating the capacity to add in things like monotonicity constraints? There are
Say that
some
again. Sorry, say
like
that
sea level
again.
we don't.
What constraint? Sorry.
Oh, like a constraint on the optimization of a model such that it only increases with time, for instance. So like this isn't something that you typically see in sea level. We don't typically have prior information that sea level only fell, although you could imagine a scenario where that happened. But in other paleo communities like the cosmogenic nuclide exposure age dating community, typically the assumption is that ice sheets only thinned from last glacial maximum to mid-Holocene. So in that case, if you were trying to use PaleoSTEM to model exposure ages, you would want to enforce that the elevation only decreased through time towards the present.
Yeah, so it's kind of like you have two ways to do that, right? So basically, for the first way is like you can add some synthetic data to force it decrease with time. I think that would be possible way. Like and the second way is like maybe you can add a prior to the parameter. It's kind of going down. So that's my first feeling about how do you implement it. I'm not quite sure how they implement it. Uh, but yeah, I think yeah, it's kind of my gut feeling about that, but I'm not quite sure how to implement it in their model. Do you have an idea? Like how do they implement it in their model or something like
Well, so there's only really one spatial temporal or one temporal model that people use in the in that community, and it's also written by Neve.
Oh, okay.
But what they but it's a spline fitting.
Yeah.
They don't use GP regression, probably because it's you have to be kind of nuanced to add in that sort of constraint. So what they do
Yeah.
is they take basically penalize the derivative so that it's positive.
Oh, okay.
Just like
That kind of
enforce
yeah.
like change the likelihood.
Okay. That you can put some hard constraint on the derivative. I think that would be possible as well. But for me, like a practical problem for us to model sea level is that we know that if we model paleo sea level, we know that the model sea level is zero everywhere. So what I usually have to do is I just input some synthetic data to inform the model that model sea level is zero, because otherwise model wouldn't know that the model sea level is zero everywhere. So this is a great question. So here we just run it. So here let's start to plot it. Okay, I should change it to 1000 because I only want from 1000 iteration. So here is like when you predict posterior distribution of your prediction, you do need to run through this for loop because we are using a distribution of hyperparameter. So you do need to change the hyperparameter and produce the prediction in a for loop way instead of just directly predict them as a noisy as a empirical based method. So here we can get an idea of the distribution of our hyperparameters, and we can plot the posterior distribution of our error invariable Gaussian process. I hope this makes sense to you. And the reason why this kind of error invariable Gaussian process works slightly better, you see here, the uncertainty range quantified by our GP cover the original true function somehow. Although you see the mean function is still not that similar to the true function, but it provides a realistic uncertainty estimate. So here just an example the performance quantification. So here you see that the original GP 68 credible interval only covers 18% of original curve. It's increased to 28% in a noisy input Gaussian process, increased to 0.29 in area invariable GP. But if you think about 95 confidence interval or credible interval, it kind of increased a lot. It performed pretty well in area invariable GP. And lastly, I want to show you why, because okay, I think I need to modify the code as well. Okay, so because of we are directly sampling the temporal uncertainty, we can have a posterior estimate of age distribution for each model. So here it's like here you can see here the red dashed line here is that it's showing us the true curve, the true age of this data point. Because we generate this data synthetically, we know the true age, and the blue histogram showing you the prior distribution of this age model, and we have like 7 data points in this example as well. So see here, for many of them, the posterior distribution fits slightly better with the true age. So that's why it's kind of provide us a better estimate of the uncertainty. I hope this makes sense to you. Okay, so now you have 5 minutes to run this code. So please remember that you do need to decrease the iteration time and sampling time to make it faster. Okay. Any questions? Let me know.
Chen?
Okay.
Oh,
hello, Sarah.
Hiya, we're looking at the graph where it has the prior and posterior ages, and there's 4, 5, 6, 7 graphs. And then there's the little clouds with the posterior clouds. Why do the posterior clouds not cover the full scope of the x-axis error? They seem to kind of be clustered to one end or the other end. There.
Yeah, okay. So this cloud here basically shows our posterior distribution of age. Okay, let me just make it bigger. Okay, so if you think about this kind of blue arrow bar, which is our prior distribution, right? The reason why this kind of moving to the right is that if you move into the right, you make the likelihood a little bit higher. So the GP so the GP model fit the data slightly better. So here is the true curve, right? But if we look at this plot, the GP will kind of consider it's a good estimate of so it's everything here is based on the likelihood calculation, Sarah. So we are basically sampling the age prior to make the data fit better in the vertical way. So basically the cloud's moving to the right because the model think if we move the age model to the right, it will fit better with the observation. So that's the difference. I think, does that make sense?
So we're counting that the like red dots are the observations we're aiming for, and the noisy observations we're just kind of not encountering the whole x-axis error or the time error. We're kind of focusing more on the fitting the y error. Is that what you're saying? Because in my mind, if that blue crosses were an actual sea level time, it's got really big x errors, and the time could be anywhere along that line.
So the x-axis also generates some information. So you put your blue histogram as a prior. So different. So if you move into the right, the prior is the likelihood. The prior probability is lower, but this, if you move into the right, maybe it contributes to a higher likelihood. So that's why it's moving to the right. But also, like, it really depends on different process level model, right? So if you have different model, process level model, the age might not move to the right. So it's kind of depends on the model as well. Oh, hopefully that makes sense. Okay, I think it's about 5 minutes. So everyone good? Everyone good? So, do you need more time? Please let me know. Everyone is able to run through this kind of stuff here to get it one. Okay, so I might just continue because we have more exciting thing about spatial temporal. So if you have